What's up, dude? How's it going?
It's good.
Skyler's new here, isn't he?
No, I'm I'm on appointment right now, so
Oh, okay.
Yeah.
I want to watch for a little bit.
Nice.
Yo,
Oh.
so everyone's cool if I record and put this on YouTube, right?
Yeah, we were
Shit.
putting the thing. A thumbs up.
This is kind of in some ways ad hoc-ish, because I'm not gonna make you sign no release form or whatever, bro. You just tell me yes or no.
That's simple. Oh, nice shirt.
You remember in school when they made you sign all those things? Wild.
Oh yeah, those video release forms and stuff like that.
Yeah. All right, let me share. Everyone can see it, right?
Yep.
Chilling. So what's up? How's everyone doing? Good morning.
Jordan's chilling. Alex is good.
All right, let's get it.
Get straight to it.
So I wanted to start with a review of linear regression and gradient descent. So we're gonna be starting off strong with this Colab notebook, which actually I need to share with all of you.
Yep.
Hold up. I'll put it everywhere. Don't worry. I'm gonna put it here on the chat, and then I'm also gonna put it on the Discord. So that everyone has access to it. This is the link to due dates. Okay. So if everyone has access to it, put a thumbs up.
Yeah, let me know if you guys have. Okay. And Jordan, yeah, they have access.
Okay.
Everybody down here has access. Nice.
Everyone in chat and on here has access. Skylar, I saw your thing.
Yeah, Javi has access. David as well.
Edward, you got it?
Yeah, I think he does. Let's see.
Okay.
Yeah, he does.
Yeah, he got it. Lit. Okay, perfect. So yeah, actually this is not the name anymore. But I want to start off with this is going to be intro to linear algebra.
Yep.
Okay. By the way, I also looked at the form that all of you filled out last time, and it seems like everyone is a junior and up.
Mm-hmm.
And there were 2 grad students in there as well. So I think
really?
yeah, I think the pacing we will take it a little bit faster than usual. Or I mean, I'll still try to accommodate for everyone, but it seems like there's a fairly good amount of background knowledge. So what do we remember from last time? What did we learn in the previous session? If anyone can raise your hand and give me a quick summary. Or anyone in the room.
I know you got this, bro. I know. Alex, you want to give it a try?
You can just tell me concepts. It's like linear regression, gradient descent.
Yeah, it doesn't have to be very specific, you know.
Yeah, so you update the parameters for gradient descent by subtracting the original weight for that like iteration or whatever minus the learning rate times the partial derivative of that that specific either the weight or the bias.
Okay. Are you talking about the update? Can you guys hear him well?
I think he said you update the parameters.
Yeah, he's basically saying that you update the weights and the bias with the previous weight minus the learning rate times the multiplication of the learning rate times the partial derivative with respect to what you're updating. right?
Okay. Yeah.
That's nice. Way to remember that, brother.
Yeah. So remember last time we looked at our first machine learning algorithm, which was linear regression, which is just a model that captures linear patterns in the data. I guess that's one way to look at it. And that's given by this linear equation here. So W's represent what exactly, and X represent what?
X is the feature and W is the weight.
Nice.
Yeah.
You said X is the
Features
feature
already.
and Y is the weight.
Yeah. So weights is, well, X would be our features for the data set, and then weights is what we are tweaking to know how important that feature is in order to fit our model well. And that's what we are actually optimizing when we optimize our model. W0 is the bias, but I just have it as W0 there. But you will see it as the bias. So Y is just our alpha variable. So if this is our model's prediction, then this would be Y hat, which is just the predicted value. But if you don't see a hat on there, usually it means
the actual model
value.
Yep.
And recall also, how did we measure that our model was doing well? We use this mean squared error function, which it's fairly intuitive. It just measures the difference between, well, the square difference. Remember, because if we didn't have the square on there, if you had negatives here and positives on another one, they would cancel out, and that wouldn't give you a good estimate. So we square it, one, to penalize the errors more sharply so that our gradients become steeper and we can converge faster. And then also it has the added bonus that we will only get positive values. So we measure the difference between our predicted and our targets to see how far off we are, and we want to get closer to the targets. So everyone's cool with this, right?
Yep. Chilling.
So now let's take a deeper look at how we actually implement linear regression. So this is like from scratch. This is like NumPy from scratch. So how many of you are familiar with like object-oriented programming in Python or in Java? Like, honestly, if you've done Java, which I think everyone here is from FIU and they've seen Java, I think doing this in a more object-oriented way, even if you don't know Python, if you know sufficient amount of Java, it will look fairly similar. So in it here, this is the constructor.
Yep.
Of the class. And so you know that below the constructor, so these are our class attributes. So I'm not going to explain object-oriented programming to you. I think most people know this by now. But the main things we want to take a look at here is, what do we want in our model, our weights and our biases? Because those are our model parameters that we're optimizing. This cost history here is mainly, not mainly, it is just for plotting. So the main things we want to understand though is, how do we optimize these weights and these biases? So first, you want to initialize your model parameters. Right now, I'm just initializing everything to 0. And how many of you have used NumPy before?
Okay, we got Jordan. Jordan's used it. I know Edward's used it. Yeah.
Okay. I think most people are like fairly familiar. I know Javier, you've seen it. Skylar, have you seen it?
I think Skylar did the thumbs up already.
Okay, chilling. So yeah, NumPy is a Python package that allows you to do vectors and linear algebra, and it allows you to make these machine learning computations much simpler. So this NP0s here just allows me to define, this essentially is an array of zeros. And so it legit just looks like this. in multitasking. All good, all good. So it just looks like this for n. And here n is the number of features that we have. So remember, if we go up, we want as many weights as we have features. So this makes sense, right? And then our bias, we just initialize to 0. There are better initialization techniques, and I will put some links if you initialization. Wow, English is hard sometimes. There are techniques. I can put a link to a research paper for all of those that are interested, but there are better initialization techniques. That has to do with actually has to do with the probability distribution of your initializations at first. You start with like a uniform distribution and that works better. But I'm not going to get into that right now. Just know that for the sake of simplicity, we're starting everything at 0, but there are better ways of doing this. So our prediction function, in here, I have essentially just made this this prediction function, which I guess will come fairly intuitive. So how do we make predictions? One, again, I'm making an array of zeros that is holding all the predictions for each specific data point. So for every example that we see, so if you had like a plot of 30 examples, then you would have 30 predictions, like one for each example, right? And we want to iterate over all of our examples. And of course, each one of our examples has their own unique set of features. So if this is all the houses in the data set, well, then every house is going to have a number of bedrooms, a number of bathrooms, it's going to have all those features. And so for us to calculate the predictions for every example, then we're also going to iterate over all the features in that example. And in this predictions, this is, I initialize everything to 0, and now I'm actually calculating our actual regression model here. So this is just taking the weight for that feature. Oh, sorry, the weight for that feature and multiplying it by the feature itself. So if this was, again, running with our analogy of the housing example, if this is 4 bedrooms and we see that the weight for that is $30,000, meaning like our model learned for every bedroom it increases the price of the house by $30,000, then that's going to work its way into our prediction. So, we would say, okay, maybe this house will go for $120,000 plus whatever bias estimator we have. Does this make sense to everyone? I think that's fairly intuitive, right?
Yep.
But again, I don't want to assume that if it's not intuitive for anyone, then please raise your hand and speak. Speak or keep your silence forever. Or what is it? Keep your peace? I don't know. Something like that. Speak or forever keep your peace. I think that's how it is. We will learn a better way. So right now, this is an iterative way of doing it. We're going to learn a better computationally faster way of doing this, which is using a dot product. So a dot product will do exactly what you see up here. The difference is it will be more computationally efficient. Why would it be more computationally efficient? Does anyone know why it would be more computationally efficient? Anyone that knows?
I mean, I can't say.
I bet Jordan knows.
Jordan, do you remember this? Why using NP dot is faster than the for loop, the double for loop that we have here?
Because NumPy is optimized to work with data like this.
Okay.
Whereas like a for loop, not necessarily.
Okay,
It's
close. There's like a specific thing that it does.
What did Jordan say? It's optimized to work with what?
It's optimized to work with like matrices and stuff like that.
Yeah, but
close.
this
It's close.
actually has to do with the hardware itself. So this is like fairly low level. When
Just
you
like a peep.
when you go iterative, you only go one at a time. But with better hardware, you can do parallel operations
There you go.
and do, let's say, 100 summations at a time.
Mm-hmm.
So it can be, yeah, someone raise their hand, Skylar.
Can you hear me?
Yeah.
I have a question. When you say 100 submissions, does that improve the, like, I guess, time complexity of this at all?
Mm-hmm.
Yeah, it does improve
Yes.
the time complexity, just not actually, just not in the way that you're thinking about it. Like computationally, it's still O of n, but it's not the same doing O of n going one by one than going O of n. Okay, I guess the difference I would tell you is one is O of n, the other one is O of n divided by 100.
Mm-hmm.
Okay.
So in time complexity wise, it's still O of n, right? Like you can
Yeah.
remove the coefficient,
Yeah.
but in practice, the coefficient makes a big difference.
Mm-hmm.
Gotcha. Okay. Yeah, because I was wondering, because if it can search it at 100 versus 1, I wondered if that like altered the time complexity at all. But that's interesting. Okay. Thank you.
Yeah. Like in theoretical terms, it doesn't, but in practice, it does, I guess.
Okay. Got it.
Yeah.
Thank you.
So summations are every like weight times feature. And actually, I will show you sorry, this is like really getting ahead, but really like really getting ahead.
Mm-hmm.
I got good stuff for y'all today. Oh, you're freaking kidding me. Okay. I was gonna show you essentially like an optimized, like the difference between a vectorized the computational performance difference between doing it in parallel versus doing it iteratively. So okay, anyway, sorry, everyone understands this, right? I can move on to
Mm-hmm.
okay, so we've initialized our parameters, we make our predictions, right? So now we have our model. So in essence, our model is really like the power of our model is in making the predictions. So now we want to optimize our model to make better predictions, right? Let me go over the cost first. So again, this is just implementing mean squared error in here. And so again, recall that mean squared error looks like this. So we take the average of the squared error of all our examples, right? So how does that look in practice in the code? So it's actually fairly simple. By the way, for anyone not familiar with Python, these double multiplications here are to the power. So in this case, to the power of 2. So this is squared. So I'll go over this. N samples is the number of training examples that we have. So X shape. So shape is a function that tells you the dimensions of your array, I guess you could say. In our case, we have N features.
Mm-hmm.
And the rows is the number of samples.
Mm-hmm. Or observations, which are really on the
Samples, which I'll put as examples. I'll say training examples. Programmers and naming, dude, am I right? Sheesh. And then this is number of features. So in practice, it looks like a matrix. That's what we have up here. And then you have your predictions. So you will see that we're gonna iterate, that we're gonna do this compute costs quite a lot. But the predictions is, you give it your training examples, and you just ask it to give you to predict the correct values based on all your training examples. So for all your rows, this should give you the corresponding outputs. I hope that makes sense to everyone. It will make more sense if I scroll down and I show you like this here. So, okay, in this case, our feature is years of experience, and we have 34 rows. So when we make our prediction, we're passing in this number 1.1, and we want it to give us the salary. And we want to do that for every single row in here. So when we call the predictions, what it's going to do is exactly that. It's going to return all the predictions for all the examples that we gave it. Now, in a more complex example, like in a more complicated example, every row has multiple features, as you can see here. And the target that we want is going to be this performance index. So when we pass in all these features, for every example, we want the corresponding prediction. This makes sense, right? Right?
Everybody's good on mine.
Okay. So yeah, once we have our predictions, then we have everything we need, right? So we get the sum of the difference between our predictions and the true value. It doesn't really matter if you do predictions minus y or y minus predictions, I'm pretty sure. That's going to be, well, that is it is
Doesn't that matter when we're taking the gradient descent?
No, not necessarily. Okay. You're just again, you're just calculating errors. So I have here y hat, which is the predicted, and y true, which is, I mean, this is supervised learning. Remember what supervised learning means? We know the actual true outputs that it should have been, and we're using these actual true outputs as a means to like train our model. So in here, we just have the difference of our prediction squared. And so we're going to get the sum of all those errors, and then we're going to take the average to get our cost. So, then this becomes mean squared error. And then I'll rename that. Okay, so this makes sense. Now that, oh, just someone coming in. Okay. Hello, Asan. If you're just joining us, we're just going over.
Oh, what's up?
If you're just joining us, we're just going over linear regression, which we covered last time, and gradient descent. The access to the notebook is on the Discord. So let me know that you have access to the notebook, and then we're just, you can follow along. So now that we have our errors, now that we have a means to calculate our error, we know how good our model is doing. But now we want to go, we want to optimize our model knowing these errors, right? Mm-hmm. So for that, we have our gradients. And then remember that in order to update our weights, we need our gradients, because our gradients are going to tell us in what direction we should update our parameters. Mm-hmm. Should my W for X feature increase or decrease? It's really just that. Are we increasing or decreasing a weight? I know it sounds silly. I know it sounds simple, but when you actually really look at it, it really is just that. Or how are we changing this number such that that line is fitting our data a little bit better, that it captures the actual underlying pattern of the data. So for that, we first need to compute our gradients to know how we're going to adjust the parameters. Again, you're going to see very similar trends here. So we have our number of training examples, and then we're going to have our predictions. And recall, I have it down here, but recall that for us to update the weights, we had this mean squared error loss function, right? And to back up even further, remember that we're trying to optimize a function that is this loss function j, and it is parameterized. So like it has parameters w and b, right? Where w is our array of weights and b is the bias. So given that our MSE function looks like this, but now you're gonna see this y hat is actually a little bit different. Y hat essentially looks like this, where it's exactly what I showed up here as well. So our prediction is looking like this. So when we take remember also, in order to optimize a function, we need to take its derivative and find where its minimum is, right? So in this case, minimizing the loss function. Since we have two variables here, we need to take a partial derivative, because we want to know how we need to adjust the cost with respect to the weight in order to find the minimum value of this cost function. And for this, it is what I'm going to show you up there. But when you take this derivative, you see that this becomes, by the way, I wrote m here instead of n. It's really the same thing. But you're going to see when you take this derivative, it essentially becomes this function. So you can ignore the summation for now and just focus on the inside. And if you just take the partial derivative of the inside, you'll see that you get this. And the derivation for that is in the slides of the previous.
Of the previous lecture.
Now notice that for the bias, it looks almost the same, except we don't have this x term outside. And that's mainly because, recall, if this is squared, then this initially was w times, and then this x was squared. So when you take a derivative of that, it becomes 2x. And you do your chain rule, and then you'll see that you get this. So I'm not going to go through the math for that right now. I just wanted to quickly review that so that I can show you that that function that you see right there is what we have implemented here. So again, I initialize just an array of zeros for how we're going to update our DW. So it's just how we are adjusting our weights. And then you see that our DW for, so a particular weight for that feature. So for example, DW of 0 is how we're changing the weight that corresponds to. Now, it might get a little confusing because I put W0 up there, so I'm going to use 1. Okay, W1 is going to be the first feature, W2 the second feature. And so you can see what I have outlined here is that same thing that I just showed you right now, where we're taking the difference of our prediction and then multiplying it by the actual feature itself. This is just, if you're asking where is this coming from, I just showed it to you down there. This is just the mathematical derivation of the partial derivative. That's telling us our gradient of how we're going to adjust DW in order to optimize it. So DW, I mean, this is just doing the inside. Remember that afterwards, we want to scale that by the average of all our training examples. By the way, if you're wondering what this is doing right here, this is actually an element wise division. So what that means is that it's going to it's essentially going to scale that DW down by the average here. And then we do the same thing for the bias, but for the bias is a little bit simpler in this case, because you know that we just have this term on the inside, and it's just a summation of the difference of our predictions, right? And then you multiply that by this 2m right here. And so yeah, this is essentially just how we implement our gradient calculations. You see, it's actually not that hard in the code. And then of course, to update our parameters once we have our gradients. So for our weights, the gradients tell us in what direction to move. So if the gradient here, it's saying, if this here looks like 0.2, 0.3, and actually in some cases this might be negative, and then 0.4. So what this is saying is, for the first feature, you're going to add 0.2. Why is it add? We have a negative here. You move in the opposite direction of the gradient. I know that might seem confusing, but if you go back and you look at the slides, you're going to see that if you move in the opposite direction of the gradient, you're moving towards the local minimum. And so then this might say subtract 0.3, subtract 0.4, and slowly, adjusted by the learning rate, we optimize our model. So, okay, putting it all together is this fit function, which actually trains the model. And this here is mainly just for plotting. So actually, all that we're really looking at is this here, where we just need the number of training examples we have, the number of features per training example. We initialize our parameters, and then the optimizer optimize here. So for the optimizer, what we're using is gradient descent, which is what we went over. And so this optimize function right here. Now, there's a couple attributes to this class that I should tell you about. One is the learning rate, which is telling us how fast we want our model to update. And here's what happens. You might think, well, just make it like, super high and like update it a lot so that you can go quicker. It doesn't actually work like that in practice. If you update your model too aggressively, your model will actually not converge. And so it will just bounce around and your cost will actually get higher. I'm actually going to show you an example of that when we train. But you actually want your learning rate to be small at first. You see here it's 0.001. So that means from that gradient that we're getting, we're actually just going to take 1% of this direction. So we're going to move 1% in the direction of the gradient in order to just like slowly converge. And then number of iterations is just like how long do you want to run this optimization for. And then the batch size is, I'll explain that with neural networks. But essentially know that there are ways of training our model in which you take the training data and you bunch it up into batches. So if I have 10,000 examples, I might make 10 batches of 10,000 examples. And so our optimize function, which is the core function here, we're just going to run it for as many iterations as we specify. And in this case, we're not going to use a batch size. So it's really just going to be getting our gradients and then computing the cost. But again, this cost here, we're just using it mainly for plotting down here. So don't worry too much about this just yet. It is mainly in order to update our parameters. So to update our parameters, we use our gradients. It's that simple. You calculate your gradients, you update your parameters. You calculate your gradients, you update your parameters. And you just run that over and over and over again until your model converges. Does this make sense? Okay. So a little demo with just synthetic data. Which actually I should probably plot. Whatever is fine. So okay, I'll show you what's happening in this. So we're just generating like a random data set. Which, like as you can see here, it's just it's just a random function. You can see that the coefficients here. So this is essentially a line that is 3 x sub 1 plus 2 x sub 2 plus 1.5 x sub 3 plus b, which is the bias. And so our model needs to learn to fit this line, which is actually like a fairly easy problem for linear regression, since it's made to optimize lines. And then we just start off with like 100 random examples. Notice this has 3 features here. Every training example is gonna look like this, where you're gonna have I don't know, 0.2, 0.3, 0.5, etc. So you're always gonna have these 3 values, and you're gonna have n number of those. This split that I will explain this more when we get to neural networks, but it's probably good to explain it now. But you want to partition your data into a training and a testing set, and the reason that you're doing this is because hopefully the testing set is things that your model has not seen before. So if you try to measure how well your model is doing based on just your training data, it's like if I give you an exam and I gave you all the answers to the exam, and then I gave you the exact same exam and you passed with flying colors. Did you pass because you actually knew it, or did you pass because you memorized the answers? So that's the problem with like using your training data to do that. And so instead you want to test data. So when I give you a test, it's hopefully similar to what you've seen, but you don't actually know, you don't memorize the answers. So we'll get into like how you train neural networks and things like that, but it's just machine learning models in general. This is the recommended way to do it. And then I'm also gonna explain in later slides why you should scale your features. But essentially, part of it is if you have outliers and you also want like a normal distribution with your features, but we'll get over that. The main thing here is just you initialize your optimizer with the learning rate and with the number of iterations. So here the learning rate, by the way, I should explain how these classes work in Python. The number that you see here isn't the actual number. It's the default number in case you don't pass in anything. So if I were to just plainly make a gradient descent object here, these would be the default values. That's what this means. Over here, we are actually setting the values. So I'm just making the learning rate 0.1. It's actually a pretty high learning rate. And then just going for 1,000 iterations. And then we initialize our model. Then we're going to train our model just using fit. And actually, I'll show you a library called scikit-learn. And this is actually very similar to how that library does it. And then the rest is just mainly plotting to see how well we're doing. So if you run that demo example, you actually...
If you guys have issues running it.
What?
I'm letting the guys know here if they have issues running it.
Oh, you should actually make a. I don't think you have like edit access. So what I recommend is for everyone to make a copy of this notebook. So
Okay.
save a copy.
Yeah, save a copy and then run it from there.
Yeah. So you see, I mean, it's a fairly like easy. This is the actual. And so you see, I mean, it has like a fairly easy linear correlation.
Mm-hmm.
And so the model is able to see that linear correlation and plot it very easily. This is the cost per iterations. You can see that by iteration 100, our model has essentially already converged. The loss here did not change whatsoever. So it was able to converge like very, very rapidly. And you can see that by like the sharp drop in cost early on. So, okay, that was linear regression just with a simple example. Let's take a look at how we would do it with this very simple data set, which just has years of experience and a salary. So what do we expect? We expect that with more years of experience, we should see a higher salary, right?
Mm-hmm.
So right now, like the data looks like that, which you can see a very clear trend here, right? That with years of experience, like you make more money. This is a super easy pattern for the model to understand. And so if we do that, you can see that the model does capture that variation quite closely, and it converges very rapidly as well. Okay, does everyone see that? Any questions so far?
Dylan? Okay. Alex, you're good? Yeah. Okay.
I wanted, by the way, y'all should go on Kaggle, and that's where I got all of these data sets from. I also put them on GitHub. I mean, the way to make it easier to download, I put these wgets here, which will download the zip file of the data sets from GitHub, and then it will download it here. Although I won't put it in that one, it'll just put it here. And then you unzip it and you can load it in using pandas, which I don't know if y'all have used pandas before, but it's essentially a data science library for Python, which you can load in a CSV file into this data frame, which is essentially just like a table. And then this holds your values. Skylar, this is the first time you see it?
Yes, I've never heard of pandas before. I'm also
Oh,
offline.
No,
I'm
this
at
is
Trader
pretty
Joe's
awesome.
right now, but I'm looking at it. That's really cool.
Nice.
Oh, nice. Yeah, no, it's pretty cool.
What'd you say, Jordan?
And so now to show you, so that's essentially what I did. And this is just to make it easier. Like you can run this by just doing like Shift Enter all the way through. But I would actually recommend that like y'all go through this again, maybe like on your own time, and like try to implement this from scratch yourselves. Not that part, the demo part, the gradient descent part, and the linear regression part, so that you know that you understand it well. And one thing I'm not showing you today, but I will show you in the future, is scikit-learn, which you can literally, I mean, I could probably just show you now, honestly.
Well, in scikit-learn, you just end up like importing all those functions and classes, and it does it for you.
Exactly. So
But the good thing about doing it from scratch is that you guys understand what's happening, as opposed to just calling a function call and then you're like, oh, okay, this is happening in some imaginary box, So
I'll show you now with this example. I think it's here, right? Is it that? I thought it was capital.
It should
Yeah.
be. Wait,
I
what?
thought it was
Shouldn't
like,
it be linear? Aren't you? Yeah, linear regression. There you
okay.
I always import it as LR.
LR.
Yeah, I always just do that. I like to
Um,
abbreviate.
is it from scikit-learn dot models?
I think it is the model.
Yeah, so
I don't know. Listen, hold up. I don't know if I'm tripping, but I don't think there's a hyphen in scikit-learn.
Oh, whoops, it's not explain code. You can actually just straight up just be like import linear regression from scikit-learn. Man, I love living in the 21st century, bro. This is fire. See?
Yeah, it's sklearn. I was like, wait a minute.
Okay, it's linear models. There you go. Yeah, and you see model fit. So yeah, I'll just show you from this example. So first, I'm just going to use like the demo one that we've been using. So there's a different data set on Kaggle. By the way, Kaggle, you should definitely check this out.
Yep.
So I got the data sets from here. So this is that salary data set that I showed you at the beginning. And so yeah, you go on Kaggle. Kaggle has all the data sets. And you can just go on here and try out different ones. But so we have this one, which is performance of students, and then you have different features. So like number of hours studies, your previous test scores, whether they're doing extracurricular activities, how much hours of sleep that they get, whether they've practiced on sample questions, and then you get their performance index. So you can, with pandas, you can do things like describe, tells you like how many rows you have. If you see that you're missing some values here, then you might want to like have a strategy to account for missing values. You can get the mean, standard deviation, like you can get all these stats. And then here, I also just want to plot the individual features with relation to the output value that we want, so performance index. You can see that with hours studied, there's almost like a upward trend. Like the more you study, the better you do. Same thing, your previous scores. If you've previously done very well, you're probably gonna do very well. Sleep, I mean, you probably don't see it well here, but there's probably a higher concentration in here than it's just not as reflected in the scatter plot. Maybe a bar chart would be better, and that's another thing, like visualizing is better. And then sample questions practice, again, you probably don't see it here, but there's probably a higher density over here. And then this is just performance index versus performance index, so we're expecting like a very linear correlation. So we want our model to capture the patterns underlying the data here. And so actually, by the way, so you see that extracurricular activities is yes and no. The model, if you give it a string, obviously it cannot do gradient computation on a string. It needs a number. So you actually need to turn these strings into numbers. And so we can do that using this label encoder, where let's just say we'll put yes as 1 and no as 0. And that's just so that the model can be like, okay, bro, if I see a 1, then I'm gonna put extra weight on that value. Maybe we find a positive correlation that students that do extracurricular activities tend to perform better. And so we put a positive weight on that. We say, okay, maybe their index goes up like 5 points because of that, yes. And if they do a no, then maybe we find that there's 0. So correlation, so the weight is 0. Or, well, actually, it's still going to be a 5. It just depends if they do it or not. I hope that makes sense. So like, if you have 1, if you have yes as 1, and you put a weight of 5, then that means that there's a positive correlation, right? Like a positive impact because of that. If you put no, it's a 0. Okay, it's not going to improve your index. Does this make sense? I'm just trying to get you to understand like how the model is doing it. And this actually does scale up to neural networks, and we'll see how that is next class.
If I remember clearly, there's even some papers on like ways, like correct ways to like encode data. That's
Yeah,
like,
yeah, it's not.
that's like a whole separate.
Oh, and you see,
like,
I'm getting that error here because I forgot to do it. You see, at this point, array is numpy array. We convert it to a numpy array, and so if you see here, float argument must be a string or real number, not gradient descent. So, what I need to do is this. I need to run this label encoder here, and when I rerun this, bro, for real. What happened here?
Let me see.
We converted not gradient descent object. Excuse me. Yo, Gemini, help out here a little bit. Okay, so let me go back to where this is. Wait, did I use sklearn? No.
Did you not use it?
No. This is demo with real data. Oh, hold up. Now Gemini is tripping too, bro. Yeah, so we see it did convert it into this numerical representation. So I did get that error beforehand, but it was due to this, and then it had fixed it. Oh, is it because I need to run? Oh, I haven't. Have I ran this? Hope I've ran this. And then the scribe, and then these plots. And then you can see the plots, and then you can see this. And then you're not working for some reason?
What the hell?
Okay, in the interest of time. Yeah, what's up?
What did you use to generate the map? Did you just use like a library?
What do you mean the map?
Oh, the plots is
Map right there, that white one, yeah.
Oh,
Yeah, we use matplotlib.
matplotlib.
Yeah, matplotlib, pyplot.
No, it's a Python library up here, matplotlib. It's pretty lit. I love that library. That library is amazing.
Let's go to
You can make some really cool plots up there. But yeah, matplotlib. You can use it, make plots. Really cool.
Awesome. Sweet.
Yeah.
Thank
Okay, in the interest of time, I am going to skip that. I don't know what's up with this right now. But it worked on my machine, okay?
Yeah.
Anyways, moving back
to the
to
slides.
the slides.
I know that we got 9 minutes, by the way.
9 minutes? What do you
Yeah.
mean 9 minutes?
We got 9 minutes left.
I thought it was till 12:15.
I thought it was to 12. Okay, never mind. Oops. Okay, keep going.
Okay, logistic regression and like speed running logistic regression. So apologies.
I didn't want to do this, but okay.
So classification problems. Okay, I want someone to raise their hand and tell me what pattern do they see in this data? Yes.
Like a blob.
Okay. Yes, exactly. Okay, so now let me ask you a question, right? What happens if you try to fit a linear regression model here? Like, how do you think it would do?
Probably really poorly because there's like a gap between the orange and the blue.
How do you think a line would look like?
You can't.
You can't really because it would stop, right? Like,
Well, yeah.
you'd have like two lines and like a gap. It'd be like,
Maybe if it's trying to, if you use MSC and it's trying to minimize the, like the distance between the points, maybe you will get a line that runs right through the middle. But then again, what does that tell you? Like, I don't know, like you have a blob here and a blob there. How does the line tell you
It doesn't really tell you much.
So we'll see. But assuming they use MSC, like, do you think that that would appropriately reflect the performance of the model?
No.
no.
Why not?
It's too erratic.
Okay. Fair. So what problems do you see with using linear regression for this task?
Like it's inconsistent.
Okay. And why would you say it's inconsistent?
Because you have a lot of data in one spot and then a lot of data in another spot. It's not showing any trends at all. So
Exactly.
it's kind of hard to make any deductions because you have a
You
lot.
said the correct word there, which is trend. Like you don't see any pattern in data that's linear. So this is learning to use the right tools for the right job. So if you don't see a linear correlation in your data, then your linear model is not going to do very well at capturing linear relationships because there are none. So instead, what you want is a logistic model. By the way, Joe, I've talked enough. If you want to
Yeah,
dig
I was like, all right, guys. So this is when we get into linear regression. I mean, logistic regression. Oops. It's just a classification algorithm that is used where the response variable is categorical. So it'll be like true or false, yes or no, green, blue, red, and that's getting when you're getting into multiple colors, it becomes more of like a multiple logistic regression instead of a binary logistic regression. The idea is just to find the relationship between the features and the probability of a particular outcome. So yeah, one thing that is differs with the linear regression is that which predicts continuous values. Logistic regression outputs probabilities on an interval from 0 to 1. It's widely used in classification, so spam detection, tumor detection, customer churn, many examples of classification. And now we're going to get into the math of logistic regression.
So I just really wanted to like add, so remember from linear regression, we wanted to answer the question, how can we use X to predict Y, where X is the given information and Y is the information we want to know. So in logistic regression, you're actually trying to answer the same question, but this time the output is not a continuous number like the price of a house, it's a probability. So you want to know the probability of Y given X, which if you take in statistics, like, we can express that like this, P of Y, the bar means given X. And so to continue with the house analogy, perhaps you want to answer the question, what is the probability that a house will sell given all the features of the house? So like the rooms, the bathrooms, etc. And like, I guess you can express that as P of it's going to sell given that, X has these features on there, right?
Yeah, definitely. Okay. Has anyone seen this function before? Down up top. Okay, Jordan. Yeah, of course. Jordan, seen it? Anybody else? Anybody down in the chat? Okay, so Edward's seen it. Nice. All right. Okay, so this is the very famous sigmoid function. All right. And I don't know if you guys noticed where the input Z, what does that look like to you? Come on, you guys got this.
Yeah, Skylar.
Like a function, like f of x.
Yeah, but which function? Like, well, come on, you guys got this. Damn it! If they don't get this, I'm gonna feel so bad.
Yeah, facts.
Nah, Jordan, you can't do it, bro. You know. Guys, that doesn't look familiar to you at all? Nice. Okay, there we got it. It's the prediction. Nice.
Yeah, it's a linear regression
It's a
model.
linear regression.
It's literally a
Okay.
linear regression model.
All right, and then exactly. So where your x's are your feature variables and your w are your weights, right?
Yeah.
And it's the corresponding parameters of the model. Now the sigmoid function is a final output has a final output that is the probability that the dependent variable equals 1 or success given your inputs. This is a perfect example of binary classification. That's why we have that graph. You have some data points in the bottom. You guys can see we have some data points in the bottom, and then you have some data points up top. Where in the X bar in the X line you have your hours studying, and you just have your points there. And you're trying to decide whether or not the probability of the person succeeding. I think that's what it says, right? Yeah, or passing the exam. All right. So yeah, and then we ended up asking why does that look familiar? Yeah, and then we will see
By the
that.
way, what I just wanted to quickly say that what the sigmoid function is actually doing, like this here that you actually see, it's actually just squishing your output values to a probability between 0 and 1. So you can take that regression model that you see right here, and you apply a sigmoid function on top of it. And what you're essentially doing is like training that regression model to output probabilities between 0 and 1. So I'll show you later, but imagine that the linear line like shifts into this sigmoid function here for all the values.
Mm-hmm.
And then we'll show you what that looks like.
And this is also very important for like neural networks. You guys will
Oh,
see.
this will be very important for neural networks.
Can you go back, Jose, real quick?
Yeah.
Oh, okay, yeah. And then continue, my bad. So we did cover that. All right.
Decision.
Decision. So then we have decision boundaries. A perfect example is like you're trying to decide whether a tumor is like malignant or not, or whether or not it's benign, right? So then in here in your X, you'll have your tumor size, right? You guys can see that, right? So you have your tumor sizes, and then these are just examples, and then X is it being malignant, and then the circles is it being benign. One thing that you want to decide, so now that you have this curve, right, you want to decide at what point, right, are your values going to give you something, whether it's malignant or benign, when you're trying to predict it. So that line that you see right there is called the decision boundary, right? So you're trying to decide what's the best place to put that line, right? Because, for example, if you put it too much to the left, right, what ends up happening is that you're going to be ignoring a lot of benign like tumor sizes, right? If you put it too much to the right, you're going to be ignoring, if you put it too much to the right, you're going to be ignoring a lot of malignant ones. So you're basically training to figure out what's the right decision boundary, okay? And then we got a nice little visualization.
So this is the decision boundary noted by that essentially linear model that you have in there. So again, you see the Z is essentially a line. It's like a linear model. It's trying to find a good way to partition the data. So like if it depends where you put your threshold, but that linear model. So if you have this, like if you have this is one category and this is another category, let's say this is benign and then this is malignant for whatever, like you want the model in that Z value and that regression to find a correlation that separates those two. So I told you that linear line will turn into a sigmoid. So again, down here you have your gradient descent algorithm. And so as the model trains and it gets better, what is happening here, so these are the probabilities of your output. So there is, the true like if you have a value, you want to know if it's benign or if it's if it's malignant or if it's benign. And so you take your model, like your linear model, and you apply a sigmoid on top of it, and it gives you a probability. So when you get the output, okay, this is like, I'm 80% sure that this is malignant. Okay, so if you're 80% sure, then we're going to output malignant. I'm like 20% sure it's malignant. So, okay, if you're 20% sure it's malignant, then we're going to say it's benign. And you have a threshold, like a cutoff to say like, okay, above 0.5 confidence that it's malignant, I'm going to say malignant. And if it's below that, I'm going to say benign. So I hope that makes sense, right?
Yeah.
And the model is just optimizing for that.
Okay. And then this is the decision boundary that we were talking about. It's used for making classification decisions based on the model's output. So you're estimating parameters, logistic regression outputs a probability. That data is, that's just a different notation for W, right? So for each input, a common rule to predict, you have your prediction. It could be 1. And then usually a very common threshold is to use 0.5. So if it's greater than 0.5, you'll output 1 for the decision for the prediction. And then if it's less than 0.5, you'll output something like 0. And then in here, the threshold 0.5 corresponds to the decision boundary in the feature space of the linear, where the linear combination is equal to Z. And then that theta to the t times x is just the basically your model. I don't know if you guys look at it. You have your weight 0 plus weight 1 times x1 plus weight, and then it goes all the way to like n, right? Depending on how many features you have. Okay. Right? Wait.
So again, we want to answer the same question. I hope that you can see the trends here, but with linear regression, we wanted to know how the model fits the data well, right? So in here, we want to know the same thing. How do you know your model fits the data well? So first, let's make sure that we understand like what the objective is that we're trying to optimize. We want a loss function that is going to measure how far off the prediction probability from the model is away from the true value. So for example, if I say this is like 20, I'm 20% sure that this is malignant, and it turns out to be that it is malignant. Obviously, this is supervised learning, so we know 100% that like the true value was malignant, but you were 20% sure. So we want to get that 20% closer to 100, right? And so actually mean squared error can actually do it. Like theoretically, you can just take the difference and say, hey, I just want to get closer to this value. And it will do it. But it won't do it as efficiently and as good as more appropriate loss functions, which we use for here, one of which is maximum log likelihood, which actually it's like the loss function will be called cross entropy. If you only have two cases and it's binary, so 0 or 1, true or false, so it'd be called binary cross entropy, but it's derived from this maximum likelihood. So that function looks like this. Now, if this is the first time you're seeing this, like, please don't be scared about the notation just because you see log in there. I will give you some like insights as to why you see that log. But this H right here, whenever you see H, this usually comes from physics, where physics, you want to measure entropy. Entropy in the system tells you information about the system. If something has high entropy, then it's a bit chaotic, it's sporadic. If something has low entropy, then it doesn't have all that much information in there. It's kind of like if I tell you the sun came up this morning, okay, that doesn't really tell you much. You didn't learn anything new. But if I tell you I won the lottery, well, that's a rare event that doesn't really happen all that much, right? So your surprise is higher for one than for another. So with entropy, we want to measure that. So the surprise of our model is, hey, I'm like 20% sure that this is malignant, and it turns out it's 100% sure. Your model is very surprised because it wasn't expecting that. So that's essentially what this function is trying to capture. It's, were we expecting the value that we saw, yes or no? I hope that makes sense to everyone. I know when I say it like that, it makes sense, and then you look back to the slides and you're like, yeah, but I don't see how this fits in there. So we're going to explain that. Ignore all of the summation and everything right now. It's essentially the same thing as mean squared error. Like this is just getting like the average. The main thing is inside. So we have, and here is just the number of examples. Y here is the true label, either 0 or 1. And then Y sub I, the probability of Y sub I is a predicted probability that I belongs to the positive class. So we call that class 1. Now I'm just using 1, but it's to the positive class. So typically you will restrain it to like only measuring like the positive class, because you can derive the negative from that one, right? Like if I tell you, hey, I'm like 20% sure that this is going to be heads, what are you going to tell me? You're going to say, oh no, this is tails. By the way, I saw myself lagging a little bit. Did everyone hear me fine?
Yeah.
Okay. I hope this makes sense to everyone. Sorry for the rush. So how does this work? When Y sub I equals 1, so we have the positive class, right? And then you see that the first term here is, you know, you're multiplying 1 times the log of the probability of 1. And then look what happens to this second one. You have 1 minus 1. 1 minus 1 is 0, and 0 times anything is 0. So what you've done is you canceled out this whole term. The reason we canceled out this whole term is because we don't want to know the probability of the negative class, which is what this represents, right? We want to know the probability of the positive class. So for that, we only focus on the first term over here. Now, inversely, when you have the negative class, you see this first term becomes 0. Again, that's because this is looking at the likelihood of the probability of the positive class, which is not what we want to look at when we have the negative class here. So you want to measure the likelihood of the negative class. So you have 1 minus 0, it's just 1, and then 1 times this log, it just becomes this over here. So the reason we have these 1 minus y sub I here and this y sub I is really to differentiate between whether we are measuring the negative or the positive class. And the log inside is actually giving us the error for what our prediction. So if I show you what I did is I just plotted, or like you can just plot this function here and you can see what this looks like. So here's what the function looks like. When your true value is 0, if you output 0, then it's gonna, the log of 0 is gonna be 0. Log of 1 is 0.
Yeah.
And so to know what that is, so the log of 1 minus 0 is log of 1. So that's going to be 0. Why? Just a reminder on exponentials. Anything to the 0 power, although with some things on 0. But if you have 5 to the 0 power, it's 1, right? We know logs and exponentials. Log is the inverse of an exponential. So yeah, when you have a 0 and you correctly output and you say, hey, I believe that the value is 0, then you're getting a very low loss here. But conversely, on the other side, if you output that the true value is very close to being a 1, this here asymptotes to infinity. So you're going to really penalize the model for getting things wrong. And so if you take the slope of the tangent line here, you see that that gradient is very steep. So this is actually helping your model converge faster because you're going to have stronger gradients directing your model to where you need to go. You're telling the model, hey, look, you need to go here. And right now you're like predicting over here. So it's going to like sharply go down. The same thing happens when your true value is 1. If you correctly output a 1, okay, good. Then we don't have that much loss. But if you output something close to 0, it's going to asymptote to infinity. And so everyone can see this, right? This is how our loss function looks like. Intuitive, I know it might seem scary. So again, for anyone unfamiliar with the term, actually, I'm going to skip this in the interest of time.
Yeah.
I'll intro to linear algebra real quick. So I want to explain this dot product. So why do we want to explain this dot product? Quick question. Does this down here look like anything to you? You keep seeing this. Hello?
Yeah, we heard you over there. We were waiting for someone.
Yeah. But I asked the question, does this look like anything?
Yeah.
So it looks like a linear regression model.
Yep.
And we then saw that that linear regression model was also inside of the logistic regression model. So it seems to be fairly important. We want to know the sum of the linear combinations of our features and our weights. Now you can do this with something called a dot product, also called like scalar product. And it's equal to the length of the vectors. I think you can also see, there's also like a more geometric approach to it, which is looking at it here, which is you take the and actually this is how you can measure later on when we get to cosine similarity. You can see like when you want to see that your embeddings are close together, like you can use this, but that doesn't make any sense to you right now. You can see how far off two vectors are from each other by noticing the angle between them.
Mm-hmm.
If a line is right on top of itself, then it's the same line.
Yep.
If a line is 90 degrees from itself, then that line is perpendicular, right? Joel, sorry, did you want to take this?
I'll take the next one. Just finish this.
Okay. I'll just let you do the next one.
Okay. Oh, and then this is a little animation I did so you guys can see what dot products are doing. There we go. We have two vectors. You have the angle. Yeah, I'm cooking with Manon. Let's go. And there you go. And then that's the geometric interpretation of it.
So I will say that in practice, this A with the little arrow and the B with the little arrow is going to be the let me jump straight into the Colab notebook to show you that actually, and I could probably just go here. So with logistic regression, yeah.
Is the dot product similar to the linear progression and the logarithmic one as well? Like, is it similar how they're used, or is dot product something different?
Yeah. So you want to take that one, Joes?
Yeah, so like the linear, if you notice that can we go back so you can see the formula?
Yeah.
Yeah. So, where is it? Yeah, right there. Why do I have this like emblem thing in there? Like, what the heck is that? Okay. Yeah. So if you notice, this looks very similar to our linear combinations, right? Of our weights and features, right, Skylar?
Yes.
Good?
Mhm.
There you go. So that essentially is what dot product does. It basically gives you a linear representation of like your linear combinations with your features and your weights. So yeah, it's very important in linear regression, which is also very important in logistic regression because what you're inputting to the exponent of your exponential function is just a linear combination, right? If you remember that what the z was. So that's also important in logistic regression. And you're going to see that it's also very important in neural nets when we get there.
So
Awesome.
I
Thank you.
hinted at the dot product of here, if you remember at the beginning, where I did this predict, where the predictions of the linear regression model, I said we're doing it like this for now, but there's a better way of doing this, and it's actually doing this NP dot right here.
Okay.
Dot product between the features and the weights, right? And then you just add the bias. So actually, in order to like do the predictions, you can just do a dot product, and that will tell you the predictions of a linear regression model.
Nice.
Yeah. So it's very useful. And then there's also some more like mathematically intuitive things behind it. So the same thing with the sigmoid function here, like when you predict, you see how you have this linear model, which is just the NP dots. And then it's the same thing as I had up there, which is you have your training parameters, so like your training example and then the weights,
Mm-hmm.
and then you add the bias. So actually, you see that a logistic model is actually just a linear model, but you apply the sigmoid on top of it, because what this sigmoid did is it transformed all of the outputs here into a probability.
Okay.
Yeah, so the sigmoid is really just there to go from like continuous values to probabilities.
Awesome.
Yeah.
Sweet. Thank you.
Yeah.
Jose, it's 12:17. Do you want to continue the Colab notebook for like
For next time.
for next meeting?
Yes.
Yeah.
And
So we got some more stuff to go. Yeah.
we had some more fun stuff for you, like matrices, but it's okay. We'll cover these with neural networks next time. Yeah.
And then we'll also talk about we'll cover them with neural networks, and we'll also talk about another way to like measure entropy. which is like cool, which is KL divergency, KL and divergence, my bad, not divergency. And then we'll talk about entropy a little bit more. So yeah. Any questions, guys? So far, so good. Okay. Yeah, everybody down here is good. Nice. Thank you, everyone, for joining. We'll see you guys next week. Feel free,
Thank you,
feel
guys.
free to like work with the notebook that
Yes.
Jose provided. Try to make a copy, remove the code, like, and then leave the comments, and then try to see if you can implement that code yourself.
Real quick, could
Yeah.
Jose drop the slides in the Notion?
Yeah,
Thank
yeah,
you,
we're
guys.
gonna be inputting them in the Notion. Yeah, yeah. Okay. All right, guys. Thank you for joining. Jose, we'll talk. I gotta go to work, bro.
That sounds good.